Hello students, today I shall discuss about subspace. So section 2 subspace definition 1.2.1 that V over F is a vector space and W is non-empty subset of V. Then W is called subspace of V if W itself forms vector space under the induced operations of V over F. That is under addition and scalar multiplication under which V is vector space. Under those two compositions, W must satisfy all the conditions of a vector space. Then we say W is subspace of V. Then theorem 1.2.1, if W is non-empty subset of vector space V over F, which is closed under addition and scalar multiplication, then W is subspace of V. Proof: we are given W is closed under addition means x plus y belongs to W. W is closed under scalar multiplication means alpha x belongs to W. For every x y belongs to W and for every alpha belongs to F. These two properties are satisfied. Now if x belongs to W, we take alpha equals to -1 because in a field -1 is always there. So if x belongs to W, take alpha equals to -1, so we get -1 into x, that is minus x belongs to W. That is every element of W has additive inverse in W. Further, now x plus minus x will belongs to W by this property. X plus minus of x means 0 belongs to W. So additive identity is there. So both additive identity and additive inverse of every element of W is present in W. So now because W is subset of V, therefore any property which is true for elements of V is also true for elements of W. So any property which is true for elements of V is also true for elements of W. So therefore x plus y equals to y plus x, alpha into x plus y is alpha x plus alpha y, alpha plus beta into x is alpha x plus beta x, alpha into beta x is alpha into beta x, 1 into x is x. For all alpha beta belongs to F, these are for all these properties. For alpha beta belongs to F, for all x y belongs to W. So therefore W is subspace of V. Next, theorem 1.2.2, if V over F is a vector space and W is non-empty subset of V such that alpha x plus beta y belongs to W for all alpha beta belongs to F, for all x y belongs to W, then W is subspace of V. Proof: we are given alpha x plus beta y belongs to W for every alpha beta in F, x, y and W. So first of all take alpha equal to beta equal to 1, we get x plus y belongs to W. It means W is closed under addition. Next we take beta equal to 0, so we get alpha into x belongs to W. It means W is closed under scalar multiplication. So by theorem 1.2.1, if W is closed under addition and scalar multiplication, then it is a subspace of V. So therefore W is a subspace of V. Next theorem 1.2.3, theorem 1.2.3, if W1 and W2 are subspaces of V over F, then W1 intersection W2 is also subspace of V over F. Proof. First we show that W1 intersection W2 is non-empty because 0 belongs to, as W1 is subspace, so additive identity is there, so 0 belongs to W1. Similarly 0 belongs to W2, it means 0 is common element, so W1 intersection W2 is non-empty. Now let alpha beta belongs to F and x comma y belongs to W1 intersection W2. It means x belongs to W1, x belongs to W2, y belongs to W1, y belongs to W2. Because W1 is subspace, it implies alpha x plus beta y belongs to W1. Similarly, W2 is subspace, alpha x plus beta y belongs to W2. It implies, so by last theorem, by theorem 1.2.2, by theorem 1.2.2, W1 intersection W2 is subspace of V over F.